Well, let's look at some more graphs out of section 4.5. Let's look at cosecant and secant graphs. Graphs of the cosecant and secant functions. So we're going to relate the parent functions just right back to the parent functions of sine and cosine. So let's say I had the graph f of theta equals sine theta. I just want to graph that parent function. Okay. So I know that its amplitude's 1. There's no vertical shift here because this is the parent function. Okay, so there's my sine function. 2 pi. Excellent. Now, I'm going to use that to get a graph of the function, of the parent function of cosecant theta. Using my knowledge that cosecant theta, by definition, is just the reciprocal of sine of theta. Because sine of theta, remember, when you're evaluating out the sine function, you're drawing triangles, looking at the opposite side over the hypotenuse, where cosecant is the hypotenuse over the opposite. It's just the reciprocal. So thinking of this algebraically, cosecant theta, if it's just the reciprocal of the sine function, it equals 1 over sine theta. Now, that means that whenever sine of theta is 0, cosecant of theta is undefined. Because if sine of theta was 0, then cosecant of theta, that would be 1 over 0, which that's no solution. That does not exist. So I can now get my cosecant graph by looking at my sine graph. Because everywhere where sine is 0, at 0, at pi, at 2 pi, the cosecant function is going to be undefined. So I can draw in some asymptotes there. And now I can just kind of draw in where the rest of the points are on the sine curve, kind of the reciprocal of those y values. So that means the cosecant graph is just going to it's going to share the same max and min, but it's going to open the other way. So I can usually use a sine function to then figure out exactly what the cosecant function would look like. Now, I've kind of got a mess here because I've drawn one on top of the other, and I can't just erase because I didn't do this in pencil because I'm using my pen here. So I'm just going to redraw this really neatly. I've got asymptotes at x equals 0, x equals pi, and x equals 2 pi. And then, so this is exactly what the cosecant function is going to look like. There's one period of the cosecant function there, the parent function. So we could do the same thing for secant. We could take the original cosine graph, the parent function, just cosine theta, plot the function, and now since cosine of theta equals 1, since the secant of theta equals 1 over cos theta, the same logic applies here. Wherever there's a 0, I get an asymptote on the secant graph, and then I can just sketch in and notice instead of just having like half of a, I mean they look like parabolas even though they're not parabolic, but instead of just drawing in the half, I'm completing it, drawing over on the negative side, and I'm making my interval go a little bit past 2 pi by going to the right and completing what the secant graph would look like there. Okay, so I'll do a cleaner sketch down below. So our asymptotes are going to be at pi over 2, 3 pi over 2. So the picture would be exactly that for one cycle, but then of course I could just extend, because I know the picture is going to look like that, and I could add in some more asymptotes as well if I wanted to on the ends there to get more than one cycle in. So now that logic is going to follow even if we have a more complicated function. The trick is to draw the corresponding sine or cosine function first, and then use that to figure out where the asymptotes are for your corresponding cosecant or secant graph. So let's take some of the examples that we used in our other previous notes. So let's say I had f of theta equals 2 cosecant of pi over 2 theta. So the first thing I would do is I would graph. So first I'm going to graph the corresponding sine function, which is f of theta equals 2 sine of pi over 2 theta. Now we already went through graphing that in the other set of notes. The amplitude is 2, the period turned out to be 4 here. So I'm going to make a graph. Amplitude's 2, the period's 4. So I'm going to draw my sine curve. And now, everywhere there's a 0, I'm going to dash in an asymptote. And now I'm going to draw in the cosecant graph. And now if I had a pencil here, then I would erase the sine curve, because the sine curve just serves to help me understand where the asymptotes and what the cosecant corresponding cosecant function is going to look like. But I don't want people to get confused and think that the points on the sine curve are actually points on the cosecant graph, because that's not the case. It just helps us understand the properties of the corresponding cosecant function. So that's where if you have pencil, now you can erase that sine function and you'll have a perfect cosecant graph. And the same trick works for secant. You plot the corresponding cosine function, dash the asymptotes where the cosine function has zeros, draw in the secant function, and then just kind of erase your cosine curve.